picks up where we left off on the previous lesson, where we're trying to understand accelerated motion. And we're looking at two different types of graphs, position versus time and velocity versus time. The key points from the last lesson were when you have a position versus time graph, such as this one right here, and it's curving, we know that the slope is changing. In this particular case, the slope is getting less and less steep as it gets flatter and flatter at the top, and then it gets steeper and steeper once it gets past the peak. In a velocity time graph, we learned that acceleration is seen as the slope itself of the velocity time graph, and generally the velocity time graph is going to have a straight line, implying the slope is constant, which means the acceleration is constant. So let's look at a few more details, a little more complications with these type of graphs to add to our understanding. So in this first situation, we have something clearly happening where we're moving forward in time. We stop for an instant right about there, and then we start heading back, and the whole time we have a curved shape here, so we know we're accelerating the whole time. What if I ask you to find the instantaneous speed at any given time? Let's say, for instance, after 2 seconds. If I go up here to 2 seconds and put a mark right about there, you could say, alright, we've gone 10 meters in 2 seconds. 10 divided by 2 is 5. Is that our instantaneous speed? And the answer is, that's correct. No. The speed has been changing the whole time. It's slowly getting slower. So the 10 divided by 2 is just the average for the entire interval. So how on earth do we find the instantaneous? Well, it's actually a little bit complicated, but we just want to point out to you that if we were to draw a tangent line right there and find that slope, we would get the instantaneous speed. If we want to know how fast we're going at the very peak of this graph after 6 seconds, which corresponds to a position of 18, it wouldn't be 18 divided by 6. That 3 would be the average from the beginning to the end. Instead, if we draw a tangent line, we see that tangent line is flat. In other words, we're not moving at that instant. Okay, so to sum up, if you're ever asked to find the instantaneous speed, you draw a tangent, okay, and then you calculate its slope. We won't have to do that, but I thought you should be aware. Okay, now let's look at these graphs from more of a conceptual point. So let's get rid of these tangents. Okay, next bullet. A decreasing steepness indicates, okay, so where is our steepness decreasing? It's not right here. The position is going back, but what steepness is, again, looking at those tangents. So I draw a rough tangent there, a rough tangent there, and then a rough tangent there. We see that the steepness of those tangents are getting less and less. And if we keep going, now we see that they're getting a little steeper. They're going from flat to a little steeper. So decreasing steepness indicates slowing down. And you see it on the first part of that. A decreasing position, on the other hand, tells us something else. So if our position is seen on the y-axis, position is getting greater, 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 greater. It hits a peak, and then we see it turning around. So a decreasing position indicates a negative velocity, not a decreasing velocity. Negative meaning we've gone in the other direction. So if we look at the slopes of these two lines, they're negative. So we see that we have a change in direction. Okay, algebraically, what does this shape tell us? Okay, well, it's a parabola. All right. It's an upside down parabola, but that doesn't change anything about it. Okay, and so we've learned that since it's a parabola, we know that the distance, the y-axis, is proportional to the x-axis squared. In this case, the x-axis is time. Okay, that's a really important relationship. What this means is, if I want to look at the ratio of distances at any two time intervals, it's equal to the ratio of the time interval 1 squared, this is supposed to say squared here, divided by the other one squared. So for example, at the 2 second interval, for a 2 second interval, time of 2, let's say from 6 to 8, right? So from 6 to 8, we have traveled from 18 to 14. 18 to 16. So we've got a displacement of 2 meters. If we look at a 4-second interval, in other words, moving for twice the amount of time, in other words, from 6 to 10, so again, here's 6 where we're starting at 18, and if we go to interval 10, right, our position is 10. Okay, so 18 to 10 is 8. Now, let's see what that means. If I were to do the ratio here, okay, let's say 2 over 8, right, distance 1 over distance 2, equals my time interval, 2 seconds, squared, divided by my other time interval, 4 squared. Does that check out? 2/8 is 1/4. This would be 4/16, and that's 1/4. And so we verify that the ratio of distances traveled when you're accelerating is equal to the ratio of the square of the times. So an important fact is 2 times the time gives us 4 times the displacement. So look at that again closely. Do it for yourself. Maybe choose 2 other time intervals. Remember, if you're starting at 6, that's kind of like 0. And then if you go 1 second, you go a certain distance. And if you double that time, we should see 4 times. Check that out for yourself. All right, so let's move back to velocity time graphs. All right, so here is a velocity time graph. All right, you just got to be careful of what you're looking at. So we're literally looking at velocity. So at the very beginning, we're already moving at 6 meters per second. And then at some time later, 6 seconds, our velocity is 0. And then at the end of this interval, our velocity is -4. So we can determine some interesting relationships between average speed and instantaneous speed using this. So let's say how can I put this? If the beginning of our interval, let's say from here we started at 6, and right here we're moving 0, okay, so v equals 0 here, and initially our v equals 6. We can ask ourselves, what's the average velocity during this interval? Okay, so we could say, well, we started at 6, we were at 0, we were at 5, 4, 3, 2, 1, 0. So we can say that the average velocity when we are changing speed is the initial plus the final divided by 2. So that's another way of looking at average velocity. It's initial speed, vi, plus vf divided by 2. We're just taking the average. And this assumes constant acceleration. In other words, the rate at which we're changing is constant, and we can see that by the straight line all the way through. Okay, so I've already done that here. So what is the average velocity from time 0 to time 6? It was 6 plus 0 meters per second divided by 2, which is 3 meters per second. Now in a position time graph, that actually is useful to know. In this case, we went from 0 to, or excuse me, if our initial speed was 6, right? How do we know? Because this graph is the same as this graph. So our initial speed is 6 here. We know at time 6 our speed is 0, right? And we also know that the tangent of that slope is flat. Okay, so if we are to ask you what's the average speed from beginning to end, right, we know we could do distance divided by time. We've gone 18 meters in 6 seconds, so 18 divided by 6 is 3 meters per second. And we know we started at 6. So what we can deduce from that is that your instantaneous speed at the when you have a position time graph is equal to twice your average speed. Alright, so in this graph, if you calculate the average speed for an interval to be 3 meters per second, and it's gaining speed, the instantaneous is going to be double that, or 6. Okay, the last thing is kind of abstract, the area under the graph. Okay, so you might think, well, what are we talking about when we mean area? So let's erase that. Alright, so let's say I want to know the area for this graph for the first 6 seconds, right? Look, from here to here. So the area would be this triangle, what's bounded by the graph and then the axes. And if I want to do the area of this, it's a triangle, so I'd say the area of the triangle is 1/2 base times height, right? Now let's translate that into our variables. 1/2, well, what does our base represent? It represents time. And what does our height represent? It represents our velocity. And so, if you recall from our first set of equations, velocity times time is nothing more than displacement. So you can figure out how far you've traveled with a velocity time graph by finding the area under any part of the curve. Okay, so in this particular case, we can say after 6 seconds, 1/2, our base is from 0 to 6 seconds. So 6 seconds. Our height is 6 meters per second. Okay, multiply that all out and you get 18 meters per second times seconds gives us meters. And sure enough, if we go over to this graph after 6 seconds, we see that we've gone 8 meters. Alright, let's try this again with, let's say, from 6 to 10 seconds. So let's say we go from here to here. Okay, so our area becomes the area under this one, which is between it and the x-axis. So it's actually area above the triangle, but it's the same idea. So we want to look at that. Again, it's a triangle, so we do 1/2. Our base is from 6 to 10, so that's 4 seconds. Our height is from 0 to -4, so I got to put in a -4. And we'll get -16 times 1/2, -8 meters. Now that negative might throw you off. You can say, how can I get a negative area? Well, remember, the area represents not a literal area, but the displacement. So during this interval, we've displaced ourselves 8 meters in the opposite direction. And if we look at this graph, we started at 18 and we ended up at 10. So our displacement is 10 minus 18, -8. We've gone backwards 8. So it gets a neat little verification. So if we put these two together, these two areas, we would say our total displacement is 18 plus -8, which is 10 meters. And our total distance is the absolute value of those, right? It's the absolute value of 18 plus the absolute value of -8, which would be 26. And so if we go back to our position time graph, we've started here at 0, we finished here at 10, so our displacement is 10. But we've gone a total of 26. So it's kind of cool how you can use the area of this graph to find displacement. So that's an important point. It's not obvious, but pay attention. All right, the last thing, what is the acceleration during the same time intervals? Okay, so we can't forget that acceleration is the slope. So let me just change something about my pen. I'll go to a different color. All right, so our slope is change in y over change in x, right? So I'm going to choose 2 points on this line. I'm going from 0 to 6 seconds, so I'm really finding the slope between here and here. That should be pretty straightforward. So it's 6 minus 0 meters per second divided by, whoops, and our time is 6 minus 0 seconds, which gives us 1 meter per second per second. Okay, so we're slowing down at a rate of 1 meter per second for every second. How about this time interval? Well, I'm hoping you're anticipating what the answer is, because if you notice from here to here, the slope of the line has not changed. So it's the same acceleration, even though we are slowing down at here, and then we're gaining speed from 6 to 10. But let's verify. So I'm going to go from the end point to the beginning point. So my final velocity is -4. Minus initial velocity of 0 for that interval, minus, or divided by, my end time is 10, and my beginning time was 6, minus 6 seconds, that's meters per second. So we see -4 divided by 4 is -1 meter per second. And I guess I wasn't careful right here, because this should have been, oh, that was bad on my part, 0 minus 6, our final minus initial, so we should have -1 as well. So we get -1 meter per second for both intervals, which also implies, and this came up in class the other day, at this time the acceleration is still -1. The slope is the same the whole time, even though our velocity is 0 at that point. So to put this all together, if if we were to describe the motion for this entire 10-second interval, we're initially moving away from our starting point. We are not headed back to the starting point while I'm here. We're just going faster and faster, or we're going slower and slower and slower and slower, but still moving away. Then when we get here, we're stopped, but we're changing, so we're still accelerating, and then we turn around, now we're in a negative velocity, and we start gaining speed. Even though this looks like it's going down, it shows a gain in speed. We're going from 0 to 2 to 4 in the opposite direction. And if you go back up to the original graph, that's what we said. We're slowing down, but moving further away. We come to a stop for a second, then we turn around and start gaining speed. So to take this and translate it to that, it's not easy, but they're consistent. So pay close attention to those and come in with questions.